Hi, this is lecture number 4. And last time, if you remember, we came up with a Robo-Kick. I hope you remember. And this time I'll take a look at that Robo-Kick from robot point of view. So, what we have had last time, at the very end of the last time, this is what we had. Nothing wrong with that mathematically, except that there was a little note there. This one here is changing all the time. All right. So this is a fact when you really actually controlling a robot or the joint. We have 3 phases. One of them is to accelerate. So from stop to accelerate to speed up, and then constant speed, and then slow down to go to the target position. So if we follow this type of control of your motor, then what can we do? Okay. First of all, since you have 3 phases, I will divide the time interval into 3 intervals. Well, from 0 to 1, 1 to 2, and 2 to 3. How about that? That's easy. Well, actually, that's the reason why I chose 3 seconds. It is easier to divide. And we do different things in the different interval. So what it amounts to is that we choose different function for different interval. So what do we use? Well, if you remember, the second order polynomial was useful. So why don't we use it again? Okay, something was useful, so we're going to use it again. That's engineer's maximum 3. The third one. That is, there is a second fish on the willow tree. Haha, what is this? Fish, willow tree? Well, what it amounts to is that if you catch a fish on the willow tree, you will catch another fish there, is what it says. So if you translate that into engineering jargons, if a tool was useful once, then it will be useful again. That's why it is worthwhile to have many tools. Okay? So we're going to use second order polynomial, 3 of them. 1, 2, 3. Okay? So with that, we take a look at the number of parameters here. Originally, the last time we had 3 or 4, right? But this time, 1, 2, 3, 4, 5, 6, 7, 8, 9, total of 9 parameters. So it seems to be that we need to have 9 constraints or 9 conditions or 9 equations. Well, those conditions are already known. We have already used it. And new conditions are there. Angle is continuous. Of course, angle doesn't change all of a sudden, right? It doesn't happen. And angle at t is equal to 1, we don't know yet, so I call that p. And angle at t is equal to 2, this one we don't know neither, so I call that q. And according to the robot control, motor control, the second stage, you have a constant speed. So that's what I'm going to do. This part here, constant speed. Okay? So, total number of constraints, 1, 2, 3, 4, 5, 6, 7, 8. Haha, it's not 9. Well, actually, condition number 5, angle is continuous. That condition can be used both here and there. So actually, there are 2 conditions there. So all together, that's 9 is equal to 9. So we should be able to solve for every parameter. 1, 2, 3, 4, 5, 6, 7, 8, and this 5, we can write down 2 equations. So this is what we come up with. 1, 2, 3, 4, first 4, and 5 at time t is equal to 1 and time t is equal to 2, and those all everything. Here, we use this new notation, 1 plus 1 minus. Are you familiar with those? If not, those minus and pluses are for just before and just after whatever the value is. So, for example, 1 minus and 1 plus, meaning right after and just before time t is equal to 1. Okay? So, if I write down all of those conditions in terms of the equations, this is what we got. So, as you can see, theta 1 minus is before 1, so therefore we use the equation for the first interval. And 1 plus is in the second interval, so we use the equation for the second interval. Blah, blah, blah. Okay. So you have enough number of equations. Go ahead and solve. Well, that is part of the homework, so I'm not going to do it. But you can use whatever the method you like to solve, and you come up with this set. So put them together into equation. This is what you got. Well, nothing wrong with just leaving here, but I changed the equation a little bit more so that we can understand more about it. Okay, the first one doesn't change. Second one, this tells you that this term here has t minus 1. So when t is equal to 1, this disappears. So it's p. T is equal to 1 at p. So it is easier to understand what's going on. T is equal to 2, that becomes 1. So q minus p plus p, that's q. Okay, so it is easier to understand, especially the third one here. Q minus 30 is common to everywhere, so I took that one out. Then you have t minus 3 squared, and the rest is 30 degrees. Wow. T is equal to 3, this one drops, so you have 30 degrees, right? Okay. Okay, so let's plot this one here. And, well, we're going to plot that one to see that. I mean, I'm going to show you a little bit more on that. But before that, we still have P and Qs. We haven't have any number for it, right? So to plot it, we have to put the number to it. So we need to choose. Then whenever you choose something, you would ask that, is there a good pair? Which is good? What numbers are good for P's and Q's? The best one, I call that star here. Whoop. Star here. Okay? So if there is a best choice, how can we find it? Try some pairs. As I said, this is going to be homework. You are going to plot different curves by changing the values of P's and Q's. Okay. Well, anyway, obviously there is an answer that there is a best one, best choices. So how can we find it? Question number 3. Okay. So this is the type of homework I will give you. This is an example. So here, choose at least 3 pairs of P's and Q's and plot them where this constraint is satisfied. Well, obviously, P's and Q's are within minus 60 to 30, and P is smaller than Q. That's what it says. But if you don't use this one here, that's P3, okay, without a constraint. So you're free to choose any P's and Q's, up and down, whatever you like. Be imaginative, be inventive. Yeah, get your own original ones. And also, for both of them, plot theta dot, speed, and how speed changes. This is the type of homework I will give you. The homework set is available in a different place. Okay. The one thing you're dealing with is actual robot or actual motor. This is a very, very important fact that sudden change in the speed is bad for motors. If you try to change the speed all of a sudden, the motor has to generate a lot of force, meaning that the motor will heat up. And heat is really bad for the motors. So you don't want to do that. Okay? And you must have found, well, if you have done that homework, you must have found that some of the speed profiles has sudden jumps in the speed. So I want to get rid of those jumps in the speed, meaning that I would like to make the speed be continuous. If we can do that, then there's no sudden change in the speed. So this should be okay. So for that, what I do is not just theta, but theta dot. I will make the speed continuous at t is equal to 1 and t is equal to 2. If I write down using equations, those are the equations we have. And using p's and q's, I will get those equations. And simplify that equation, we get this one here, and well, that's two unknowns and two equations. Easy to solve. And p is equal to 37.5 negative, q is equal to 7.5. So putting those values back into those parameters, then you get this set of equations. Okay? So let's check this one here. Well, one thing you should do all the time is that whenever you do this type of derivation, you may make mistakes. I make mistakes. So whenever you get the answer, you should check the answer before you actually move the robot. Because I do remember my students, plural. Many students broke robot because they didn't check. Okay. So that's theta dot speed. Okay. And if you take a look at 1 minus and 1 plus, 2 minus and 2 plus, those are all 45, so it's continuous. Okay, that's great. It is sound. So speed is okay. All right. So let's plot it. Well, actually, if you plot it, you can tell. This is theta, this is theta dot. So theta dot is continuous here and continuous here. Okay. So and these are curves simple and beautiful. Simple. Why? Why is this simple? Okay. Well, in the next slide, I'm going to talk about why this one is simple, etc., etc. But before that, let's take a look at the ball kicking. Once again, 0 degrees and 1.8. So the timing of kicking the ball doesn't change. Okay, although this one has a little bit of kink to it. Okay. Comments. Continuous speed meaning smooth curve. That's nice. There's no corners in the curve, the angle. And this is a typical robot motion: acceleration, cruising at a constant speed, and deceleration. Right? Acceleration, constant speed, and deceleration. To see that, easiest way is to take a look at the derivative acceleration here. The acceleration profile is simple. So that's why I said it's simple. Acceleration profile is very simple. Constant acceleration, no acceleration, and then constant deceleration. So you only need two values for the acceleration. This one here and this one here. Those are the only two values you needed. So if you do write a program to control the motor, this is easy, this is simple. Okay. This acceleration profile is handy for motor control. More on this later. I will talk about that, and I will talk about how this acceleration can be connected to the torque and the voltage applied to the motor. Okay, motor control. So from here on, we have to look at how the motor works. So let me talk about the motor control. And I assume that we are going to talk about DC servo motor. And DC means that we are talking about battery. We use battery. And the servo, the word servo is used that something to follow command. So the characteristics of the servo motor is a fast and accurate angle response. Angle changes very fast and follows your command. That's what servo motors are. So, first question, what does a motor generate? What do you think is a motor generate? Rotation? Not so quick. It generates a torque, rotational force. What it generates is a torque, the force. Okay? And then, what is a torque generates? What is it? Then rotation, right? Not quite. It generates angular acceleration. Acceleration. That's Newton's law. F equals ma. Right? So force and accelerations are proportional to each other. So therefore, the force, rotational force, will create rotational acceleration. That's angular rotation, acceleration. And the final question about the motor is this. Voltage generates torque. That sounds really okay, but not quite. Current generates torque. This is something all robotic engineer has to know. The current generates torque. So therefore, if you want to control a motor, you need to control the current. Okay? That is it for today. And next time I will go into the mathematical part of the robot control, which is functions, etc., etc. Okay, thank you.